everything. Yeah, so we draw these things with edges typically pointing down, so the parent on top and the child below. Or if you like, the parent is closer to the root than the child is. And well, once you have the notion of parents and children, then you have the notion of ancestors and descendants. So the ancestor of a node can be its parent, or it can be its grandparent, or its great-grandparent, and so on. And the ancestor of a node can also be itself. So we'll say that a node is an ancestor of itself. So everything on the path from that node up to the root, all of those things are ancestors, including the node itself. And the lowest common ancestor of two nodes, so let's say like here, U and V, well, for that you look at all the ancestors of U. That would be these ones. And all the ancestors of V, that would be these ones. And you look for the lowest one that's common to both U and V. So these are two common ancestors of U and V. This is the lowest one. And lowest kind of refers to this picture here, the way we tend to draw them. But you could also call it deepest, because the lowest one is also the one which is furthest from the root, meaning it has the largest depth among all common ancestors of U and V. Okay, so this thing here is the lowest common ancestor of U and V. So for example, U might be humans, and V might be chimpanzees. And then up here, this lowest common ancestor would be the some common ape ancestor. Okay. So it comes up frequently in this notion of trees and ancestors comes up frequently in biology, where these are species trees. But we'll see that it comes up sort of naturally in all kinds of other things that are not necessarily coming from biology, but even other unrelated looking problems in computer science. So the input is a rooted and node tree T, and we want to pre-process it so that we can answer queries of the form, you give me two nodes U and V, and you return the lowest common ancestor. Okay, I think this can be a big tree. So it's a static problem. The tree doesn't change, at least for what we're going to consider today. You're just given the tree once and for all, it's fixed, but you want to pre-process it so that you can answer these queries for any two nodes in the tree. Is that clear what we want to do here? Okay. So we'll attack this a few different ways today and see several solutions that if you combine them the right way, then they'll lead to this sort of best possible solution. But one thing I want you to just draw, so I'm trying to always present things in this course where there's some underlying general technique that you can hopefully use for other problems. And last class, we saw the so-called Y-fast tree. which was a combination of a couple of things. One was an X-fast tree, which was this sort of suboptimal thing on top. It's kind of big, although it was plenty fast. And it was used to break things up into really, really small, somehow independent subproblems that were so small that we could afford to do something suboptimal with them. So this is often called the micro tree approach.
Sorry, Pat.
Yes?
So I'm the co-host, but for some reason I'm not able to let people in. Can you make someone else co-host so that they can comment?
Sure.
I'll let them know on the group.
Okay. David, you okay with that?
Yeah, sure.
Okay, let me pull up the participants. Okay. I'll admit these two. Okay. So that's a sort of general approach, and we'll see it today, kind of. But this notion of somehow a big thing and that breaks things up into littler things. So in each case, you have things that are suboptimal, but when you put them together in just the right proportions, you get something that turns out to be optimal, and we'll see that today. And in general, it's called the macro tree, micro tree approach. So usually one big thing that organizes stuff and breaks it up into tiny little pieces. All right. So we've definitely seen trees before. We used them in a few different data structures, but it's kind of unfamiliar for us for the trees to be the data. So they're usually something we build to get what we want. So it's a little bit unusual for us to actually have trees being the input to the problem. So maybe the first thing that we'll do is try and
Pat?
Yes?
I'm so sorry to interrupt you.
It's
Actually,
okay.
I had an issue and I also have a recorded proof of it. My Carleton ID wasn't working, and when I was trying to, I will even send you the recorded proof. When I was trying to press the send button, it wasn't sending the document that I was trying to send.
Okay, you can just email me about it after class.
All right. But I mean, should I email it from my other email ID? Because
You can email it to me from anywhere.
All right. Okay. Thank you.
Yeah. So let's try and maybe make this problem look something more familiar, something closer to what we understand. So here's a on the surface of it, different looking problem. Called the range minimum problem. And for the range minimum problem, the input is an array of numbers. X1, X2, and so on up to Xn. And the queries is what's called a range minimum query. It takes two indices, I and j, and it should return, and it's going to look a little bit weird. The minimum value L in I plus 1, up to j such that xl is equal to the min of xi plus 1 up to xj. That's complicated sounding, but it's not, shouldn't be too complicated. So for instance, if this is my array, x1 through x10, and so these are the values stored in the array. You give me some range minimum query like, let's say 4 to 9. So that refers to this subarray starting at index 4 and up to and including index 9. And you're supposed to find the minimum value in that array. It's 2, but it occurs twice. And what you're supposed to give me is not the value itself. I'm not that interested in the number 2. More useful to me is the index at which it occurs, but it occurs twice. So I want the smaller of all the indices where 2 occurs. Okay. So in this case, the RMQ of 4, 9, 2 is the minimum. It occurs in 2 places, and those are indices 5 and 8. So you should return the index 5. So then I'll know the value because I can just look at that location in the array. Okay. All right. That's clear. Okay, good. So this looks like a different kind of problem, but in fact, the two are quite closely related, as we'll see. And in one direction, the way to see that is to use a technique on these trees. It's referred to in the literature as the Euler tour technique, but you can also call it just depth first search if you want. And the idea is, well, you start at the root of the tree. And for this to work, we'll have to give all our nodes names. So let's give them silly names. So you start at the root of the tree, and well, there's a few ways to think of it. One is you can imagine just walking around the outside perimeter of the tree, recording the nodes that you see, including the nodes, if you see them more than once, you record them. So for instance, here, if we start walking, we see A, followed by B, followed by D. And we come back and we see B again. Back down, we see E. We come back and we see B again. Down, we see F. And then G. Back to F again. To H. To I. Back up to H. To J. And then we see H, F, B, A again for the second time, C, and then A for the third time. So this thing here is called the Euler tour of the tree. More technically, it's the it's an Euler tour of the graph that you get by doubling each edge of the tree, because you're going to cross each edge of that of this tree twice, once on the way down and once again on the way up. If you think about a node, well, the number of times that you will see that node in this sequence should be the number of children of that node plus 1. So that's the Euler tour sequence for this tree. And since you see nodes multiple times, it's helpful to keep track of the first occurrence of each node. So here's the first time we see A, here's the first time we see B, first time we see D. We've already seen B. This is the first time we see E, already seen B. First time we see F, first time we see G, already seen F, but H is new, and then I is new, H we've seen, J is new, H we've seen, F we've seen, B we've seen, A we've seen, C is new, and then A we've already seen. So that's one of these sequences, and we can store that in think of that being stored in an array. So it has indices. Each element of the sequence has an index. All right. And well, we're trying to argue that this lowest common ancestor thing has something to do with this range minimum thing. And so that means we should somehow, range minimum is about a sequence of numbers. So we need to get a sequence of numbers out of here. And lowest common ancestor, somehow this lowest has something to do with depth. And so the sequence that we'll use is actually the depth of each node. Okay. So, and depth is the distance from the root. So A has depth 0. These two have depth 1, depth 2, 3, and 4. So this looks like the depth sequence is 0, 1, 2, back up to 1, 2, back up to 1, 2, 3, back up to 2, 3, 4, 3, 4, 3, 2, 1, 0, 1, 0. Okay. So these are the nodes, and these are the depths. All right. So let's say I want to look at the range minimum, or not the range minimum, but the lowest common ancestor of, let's say, E and H. So if I look at this array, I'll look to see where that first place is that E appears. It's there. Where's the first place that H appears? It's there. And that defines a subarray of these depths. And if I look at the minimum value in that subarray, here it is, it's 1. It appears at index 6, which corresponds to B. Okay. And indeed, B is the lowest common ancestor of E and H. Okay. And that's not really a surprise if you think about it for a little bit. For the sort of the following reason. So a subarray like this, or this subsequence here, is a walk, represents a walk in the tree, right? Everything in this sequence is one node followed by one of its children or its parent. So it represents a walk in the tree. Okay, good. And it represents a walk that starts at E and that ends at H. And in fact, the only way to get from E to H is to go through an ancestor. And in particular, you have to go through the lowest common ancestor, because there's only one. I mean, if we think of just as taking a simple path from E to H, there's only one of them. It goes up to the lowest common ancestor from E and then down to H. And why is that in this walk? Why is that the lowest one? Well, there couldn't be any ancestor of B in this walk, because if that were the case, so in particular, if A were in this walk, that means that the walk was at some point at B and went up to its parent. And if you look at the way this walk works, once it goes from a node to its parent, it never comes back into that subtree anymore. So in particular, the walk wouldn't be able to finish at H. So you can spend a little bit of time to convince yourself that this indeed works. Okay. So the walk includes a lot of things, some of which are not on the path from E to H. In particular, here it includes G, but it doesn't include anything above the lowest common ancestor, because then it wouldn't finish at H. So what does this mean? Well, it means that if we write out this, do this Euler tour, we write out these depths, and for each node of our tree, we just need to remember at what index does that node first appear. Then if I want to answer the lowest common ancestor of E and H, then what I do is a range minimum query. In this case, 5 to 10. That gives me a value, so it finds the smallest depth in this range and returns the index of it. That gives me the value 6. And now I just need to look in this other array. What's at position 6? It's B. So that's the answer to the lowest common ancestor query. So if I can answer these range minimum queries on this array, then I can solve lowest common ancestor queries on trees. Is that clear? So now we can focus on this problem, range minimum. This is the kind of problem we like. It's a sequence of numbers. You give me 2 indices, and in that sequence, and I give you the index, the leftmost index of the minimum value in that subarray. Nice and clear. Seems a lot easier to manage than working on these trees. All right. So let's focus on these range minimum problems. And the nice thing about this, the particular solution that we're going to get, is that it uses all kinds of, well, it uses a couple of different solutions, including the dumbest possible ones. So we want some data structure for the range minimum problem. And well, what is the best we could hope for? Well, the best thing we could hope for is a data structure that answers queries as fast as possible. And what's faster than constant time? So we want a data structure that you give me these query indices, I and j, and it tells you in constant time the index of the smallest value between in the subarray at that position. And we would also like it to be as small as possible and as efficient to build as possible. And it's hard to imagine being able to build it faster than O of n time, right? The input data already has size n, and we have to kind of look at all of it in order to build anything useful. So ultimately, this is what we're going to aim for, is an O of n, and this is, I'll mainly talk about space, but you can build, you can also build it in this time, and this is query time. Okay, so that's a lot to ask for right away. What if instead we just focus on getting this constant query time and we don't care about the space? Yeah. So here's an easy O of n squared O of 1 solution. You create an n times n table A, and Aij is just the answer to the range minimum query for I and j. Remember, that means it's an index L between I and j of the smallest value. So just create this two-dimensional array. And this, I mean, I don't even care. It'll even answer queries if you mix up I and j and accidentally put the smaller index first. You can even make it do that. But that does it. So what is this thing? It's just a two-dimensional array of size n by n. And when you give me any query, I just look up that location in the array and tell you the answer. That takes constant time. Really easy. Okay. And the only thing to remember is the inputs to this thing are two indices in the array, and the output is another index in the array. So actually, the values that are in the array, they don't come into, they don't appear in this data structure at all. Right? It only deals with the indices. I mean, to build it, to know which table what entries need to go in the table, you need to look at the values, but after that, the data structure itself can forget about the values. Yeah. Okay. Good. Yep. No, it's just, I mean, it's just really, you have an I-axis, you have a J-axis. For I, you can have any value from 1 to n. For j, you can have any value from 1 to n. The diagonal here is when you're looking at a range of size 1. So this is, well, I mean, this will actually be, if you ask me what's the minimum between A1 and A1, it's the item at index 1. What's the minimum between A2 and A2? It's the item at index 2. But then, you know, across here, this is the minimum. This next number here at 1, 2 could be either a 1 or a 2, depending on which value is smaller, the first or the second one in the array. But you see that, I mean, there's only n squared things in this table, and each one is just an integer.
But don't they need to change, sorry, to check the range before as many ends?
Well, certainly for space, you don't need more than this.
Yeah.
And for building it, it's fairly easy to build in n squared time, because if you look at, for instance, just one row of this thing, this is asking for queries that start with the left endpoint at 1 and then finish at 1 and then finish at 2 and so on. So that's just you scanning the array and keeping track of the smallest value that you've seen and where that value is. So that's actually we saw that in class. You write a for loop that that can do that for you. So you can fill in one row in linear time, and then you can fill in all n rows in n squared time. Okay. Good. Let's try and be a little bit more ambitious and say we still want to keep this this constant query time, but we would like to bring the space down to n log n. And in fact, you can kind of think that we sort of, all of our intermediate things, we need to keep this constant query time, because if we ever make one where the query time is more than constant, it's not going to be helpful in the end for this, unless we somehow get down to problems of constant size. Okay, so that's a big leap from n squared down to n log n. Any ideas? So this is already a, yep.
Break this down to powers of size of powers. There will be like log n.
Yeah. So, so the suggestion is to do something like break the array down into somehow powers of size of 2. So for instance, you have the original array, and then you could have an array whose length is, the thing is half of that, and this is the somehow the answer to the query, the minimum of these two. This is the answer to the minimum of these two, and this is the answer to the minimum of these 4. But that actually will lead to a linear space, because this binary tree that you're making, I mean, you only have to store one answer here. So that'll lead to linear space, which is great, but it won't give you constant query time. And that's because if you give me 2 indices, I and j, then in general, the tree looks something like this. There's a path in the tree from the root down to I, a path in the tree from the root down to j, but then there are some subtrees hanging off of here. And to get the minimum in the whole subarray, you'll need to get the minimum in all of these subtrees. So that that'll give n here, but log n over here. So there's another solution that is obvious as soon as you see it, but not at all obvious maybe beforehand. And it's the following. For each I, and let's say 1 to n, we store the answer for the range minimum query that starts at position I and goes to I plus 2 to the r minus 1. And we do that for each r in 1 up to log n. So what does that look like in pictures? Well, that says we look at the array that starts at xi, and we store the range minimum query from I to I. That's a boring one. But we also store the answer to the range minimum query from I to I plus 1. So we've got this one, we've got this one, and the next one is from xi to xi plus 2, xi plus 3. So that's 4 of them, and then the next one will have 8 of them, and so on. Okay. So for each value, I can tell you the range minimum from xi to xi plus 2 to the r minus 1 for any of these log n possible values of r that matter. So that happens to mean that, well, my queries don't always look like that. But that tells you that if you ask me for the RMQ of j minus of I up to j, then how big is this thing? This is j minus I plus 1 elements. That's how many elements are in the range I up to j. If that happens to be a power of 2, then we'll actually have the answer. So xi, we'll have for xi the minimum that starts there and goes all the way up to j, if that happened to be a power of 2. But in general, j is the difference, the length of the range is not a power of 2. What can we do then? So in general, you have I, you have j. The length of this range is j minus I plus 1. If I look at the things I have pre-computed for I have, this one, and this one, and this one, and this one, and then the next one is actually too long. But one of them will cover at least half the range, right? So because the length of these things doubles each time, the last one before it gets too long will cover at least half the range. So I know now I'll be able to tell you quickly the range minimum from I all the way up to here. There's only this little bit left to cover here. Now you could recurse on that, but that's going to again lead to a log n time solution. Instead of recursing, what can you do? Yeah. So what is this thing here? This is some length 2 to the r. So if I take j and subtract 2 to the r and add 1, that will take me to some location from j, count backwards of length to length, also the same length, 2 to the r. And this particular thing, so this is j minus 2 to the r plus 1, this thing has a pre-computed value that is the range minimum from here that ends exactly at position j. So between I, the thing I have stored at I, and the thing I have stored here, I can cover the entire range. And in this case, because we're only asking for the minimum, covering it is enough, right? We get the answer for the starting at xi, going at least halfway. We get the answer starting here, going the rest of the way to j, and we take we look at the values of those two things and decide which one is the correct answer. All right, so a little bit more carefully, this is what you store. And now when you take the range minimum from I to j, you take r is equal to the floor of the log base 2 of j minus I plus 1. And now you combine the answers, the range minimum query from I up to I plus 2 to the r minus 1, and the range minimum query from j minus 2 to the r plus 1 up to j. These are things that you have pre-computed. So for each element, each index between 1 and n, you have at most log n pre-computed answers. That's how you get n log n space and constant query time. And you have to believe that you can take the logarithm of j minus I plus 1 in constant time, but it's actually the floor of the logarithm. And if that bothers you, then j minus I plus 1 is always an integer between 1 and n. You could also just keep an extra array that stores that value if you don't trust, if you don't believe you can take logarithms in constant time. You can pre-compute them all because there's only n of them you'll need to worry about. Okay. Yep.
Sir, why is it I plus 2 R?
Well, so we're storing for every integer r from, in fact, it should be 0 here. We're storing all of those answers. So starting at I, the array of length 1. Starting at I, the array of length 2. Starting at I, the array of length 4, length 8, and so on. And that's just where that array ends, right? Think of this as you're counting from I plus 0 up to I plus 2 to the r minus 1. That's 2 to the r different elements. All right, now we're getting somewhere. So we're running out of space, so let's keep track of these things. We've got n squared, O of 1. We've also got n log n, O of 1. Let's see where we can go with that. So let's forget even how those work for now. I mean, this one's easy to remember. The n squared one is trivial, and the other one is not. I mean, we can just treat it like a black box now. So let's try and now get the space down. And maybe we won't worry too much about the query time. So here's a trick. We take our array, x1 through xn, and we break it up into blocks. B1, B2, B3, up to B, and I'll write n divided by B. The reason I'm writing that is because each of the blocks will have exactly B values in it for about value B that we'll talk about in a little bit. All right. Now, I can, well, so if I'm thinking about range minima, a block I can kind of, at least at a high level view, I can summarize an entire block very easily by just looking at the minimum value in that block, and in fact, the leftmost index of the minimum value in that block. Okay, so you can think of, you know, that gives you some value yi, which is just the minimum value of bi, and that's for each I and 1 up to n over b. Okay. And let's use the n log n O of 1 solution. But only for y1 up to y n over b. Okay. So, right, this n log n here refers to, if you give me an array of length n, I'm going to use n log n space. But now you're not giving me an array of length n, you're just giving me an array of length n over b. So that means the space is O of n over b log n over b. And just to make things easier, that's not more than n over b log n. Okay. So if we take b to be something like log n, or, you know, in fact, I'll tell you what b is. We're going to take b is equal to 1/2 log n. And for simplicity, we'll pretend that log n is an even power of 2, but that's just because I don't want to have to put floors and ceilings everywhere. So let's pretend that this gives you an integer. All right. So if we do that, then when we divide by b here, we're dividing by 1/2 log n. So that's just going to be O of n. Right? We had this extra log n out here, but now b is like 1/2 log n. So this is something like 2n. So the space becomes linear now. Problem, well, it's not a problem, but we just haven't said how to do it yet. How do you answer queries? Because sort of the standard way that a query looks, something like this, you have an I, you have a J. Maybe I and J are in the same block, or maybe they're in different blocks. I think we kind of like to think of I and J as being in different blocks. It would be great if they always were, but it's not necessarily the case. But somehow that means in order to answer this query, I need to know from I up to its end of its block, I need to know the answer there. I need to know from the beginning of J's block up to J, I need to know the answer there. And then I need to know the range minimum of these things. But these things we can get, in this case it's because we have a range minimum data structure for these minimum values in each block. That's what this is. So if I can get from I up to the end of the block and from the beginning of this last block up to J, then I can combine this, the answer that I get from the data structure here, and this to get the final answer. And that's actually easy. And why is that easy? Well, because that says for these kinds of queries, they're not really range minima. They are, you know, if I just imagine this block is all that I have, all I'm asking is what's the smallest value that comes after I? And so for this particular block, there's only B queries. There's only B possible queries. Each one has an answer. In fact, you can get it by scanning the block backwards, keeping track of the minimum value. And the same thing over here. So actually, you can answer with an additional, so, think of this as so this is called a range suffix query, or not range, but suffix minimum query. And prefix min structures for each block. Each one of those structures has size O of B. It's just a list of B numbers. So each one of those has size O of B, and the number of them is N over B. So all of those things also have only size O of N. So we sort of have two things. We break it up into blocks, summarize each block by its minimum, and then use something suboptimal for that shorter list, which is still fits in O of N space. And then for each block, we don't have the same kind of problem necessarily that we need to solve. It's actually a simpler problem because it only asks for a suffix minimum or a prefix minimum. So that's an easier problem. So that looks like linear space and constant time. What's missing? Pardon? Yeah. Of course, that's the problem when you just make nice pictures like this. You forget a case, and of course, the case is, well, what if I is here and j is here? Then this range I to j is neither a prefix or a suffix of this block. We don't have a data structure to handle that. So what do you think you do? Yep. You could recurse on each block. And if you do that, so you take this block, it's of size approximately log n. So if I use this structure, it's going to give me a structure of size log n log n. And I'm going to have n over log n of them. So if I do that, then after one level of that recursion, I will get an O of n log n size structure that can still answer queries in constant time. And then you can say, well, that all sounds familiar. Maybe I can do the same. I mean, the reason I chose the block size to be log n was because I happened to have a data structure of size that had this n log n overhead, so that made it linear. So now I could recurse again with a block size of log n, and that would put a triple log here. But each time you do that, the constant over here is going up. And if you take that to the limit, you get something like n log star n over here. But we want to cut that off sooner. We want this. We're willing to do this for one or two levels, and then we want to do something different. Okay. Now, what's the different thing we're going to do? Well, we're going to cheat a little bit. So what I need now, the only thing left is for me to be able to answer queries I and j where I and j are in the same block. So now we're going to cheat a little bit and remember where we came from. Where did we come from? How did we get to all of this? Why were we even studying range minimum queries? We were studying range minimum queries because we were trying to solve lowest common ancestor queries. And this Euler-Tor technique gave us a sequence of numbers And somehow answering a range minimum query on that sequence was somehow gave us the answer to the lowest common ancestor query. Now, if you look at this sequence here, is there anything special about it? Is it just some crazy sequence of numbers? Yeah. So this isn't just some arbitrary list of numbers. If I look at two consecutive things in this sequence, they differ by exactly 1. And that's because the walk in the tree either goes up 1 level or decreases the depth by 1, or goes down 1 level. Never stays at the same level, and it never goes down or up by more than a single level. So this is sort of a special version of this problem that we'll call the plus or minus 1 range minimum problem. So for now, let's settle for solving that problem. Okay. And so if I look at this thing, what do I see here? Plus 1, minus, or the ones get annoying quickly, so let's just do pluses and minuses. So that's plus, plus, minus, plus, minus, plus, plus, minus, plus, plus, minus, plus, minus, 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 plus, and minus. Okay. So that sequence here is actually, you can, this sequence of pluses and minuses tell you the same information. In particular, that sequence and knowing that the sequence starts with a 0 gives you the whole sequence. All right. Now, and even more than that, if I don't know that the sequence starts with 0, I even then still have enough information to answer range minimum queries. Because remember, range minimum queries, they don't want to tell you what the value of the minimum is in the subarray. They want to tell you the index of this thing in the subarray. So if you imagine what's happening here, this is just something, some sort of step function that either walks up or down at each point in time. And a range minimum is just, you look at a slab here and you ask, well, where's the lowest point on that thing? What's the index of the lowest point on that thing? And that doesn't change whether you start here at 100 or you start at 1000. As long as the shape of the walk is the same, it's going to be the same answer. So somehow, even the numbers didn't matter. All that matters is this plus and minus sequence. All right. So now we're going to do something really silly. We're going to use this solution for each block. Okay. I'll erase this now. For each block, B1 up to Bn over B, use the O of n squared O of 1 solution. But these things only have size B, so that's going to be O of B squared O of 1. And B here is, I think I had written it down somewhere. B is going to be 1/2 log n. So that's going to be O of log n squared O of 1. Well, that's not good enough, because now if we multiply by n over b, we're going to get an n times b, and nothing is going to get any, because we have n over b of these things. Nothing is going to get any smaller. But take two different blocks, bi and bj. The data structure that I use for bi is completely determined by the sequence of pluses and minus ones that occur in this range in the array. The data structure that occurs for bj is completely determined by the sequence of pluses and minus ones that occur in this part of the array. If those two sequences are the same, then bi, the data structure for bi and the data structure for bj, it can be the same data structure. So there's some table, if these two sequences are the same, then there's some table of size b squared, and both bi and bj can use that table. And that's what we'll do. Anytime two things have the same sequences of pluses and minus, two of these blocks, then they can use the same table. Or another way to think of it is just list out all the possible sequences of pluses and minuses. That's just a binary string, right? There's only two different values of length b. And then for each block, look at which, and make a table for that sequence. And then for each block, look at what its sequence is and have it point to the appropriate table. So the only question is, how many of these sequences are there? Well, the answer is there's only, it's actually 2 to the b minus 1. But for ease, I'll say that's not more than 2 to the b. We picked a very specific value of b here, which was 1/2 log n. The number of different data structures that I could need, the number of different tables that I could need, is only the square root of n. And each one has size b squared. And what's b squared? That's log n squared. And that's actually way smaller than n. So all those tables sitting off somewhere, there's only a square root n of them, and each one only has size log n squared. All of that together is much smaller than the rest of the data in the whole structure. Okay. So the last step then is to use, well, it's written here. For each block BOI, use this solution. So in total, this makes square root n tables, each of size log n squared. And so each block then just needs to have a pointer to its the table that it uses to answer these things. So that's the final step to answer these short queries that only span, that don't span any blocks. Both I and j are in the same block. You just use a lookup table that this block points to. All right. Yeah.
Say for each block,
Yep.
so how to get that? Do you have like a separate binary search block, or is it one tree for every element?
I mean, you don't even need a binary search tree. Just imagine convert this plus or minus sequence into an integer. Pluses are ones and minuses are zeros. You get an integer of a specific number of bits. That's what you call that particular block. If two guys have the same integer, then they can use the same data structure. And there's only a root n of these integers. Okay. So that finally gives you linear space and constant query time. For, let's be careful, this was supposed to be a data structure for the range minimum problem, but actually this only solves the plus minus one range minimum problem, which was good enough to solve lowest common ancestor queries. But now that we got this far, let's get greedy and try and solve the whole. I mean, maybe these range minimum queries are useful for other things and not just these special plus minus one ones. Okay. Well, here's where things really turn around. The general range minimum queries. So let's see what we've done. We took the lowest common ancestor problem and we reduced it to plus or minus one range minimum problem. But then there's the general range minimum problem that we didn't really solve because we made use of this special property. It turns out you can reduce that to the lowest common ancestor problem. And the idea is very simple. Let me just give you a bunch of numbers. So here's a list of numbers. This is the x1 through xn. That's just a general problem for range minimum queries. Notice it doesn't have this plus minus one structure. The numbers differ in weird ways. So I want to say that I can turn this into a lowest common ancestor problem. And the way that you do that is you find the range minimum for the whole array. Okay. And it's useful then to remember indices. Where is the range minimum for the whole array? Well, the minimum value is 1, but it appears twice. So we want the smallest index where it appears. So the answer is 4. So we're going to make a tree whose root is 4, the index of this thing. It's going to be a binary tree. It's going to have a left subtree and a right subtree. Its left subtree will be whatever tree you get when you do the same thing recursively on this, these elements 1, 2, 3. And over here, it'll be whatever you get when you do this recursively on these elements 5, 6, 7, 8, 9, the subarray over here. So let's quickly do it. 752, the smallest value is 2. Its index is 3. That leaves us with 7 and 5. The smallest value is 5. And its index is 2. That leaves us with a 7, and its index is 1. Now on this side, it's everything from 5, indices 5 through 9, and there the smallest value is 1. The index is 9. That leaves us with these things. The smallest value is 2. The index is 8. Leaves us with these things. Smallest value is 4. The index is 7. That leaves us with these ones. Smallest value is 6. The index is 5. And then finally, over here, we only had this thing, which is 9, whose index is 6. Okay. So this is the tree we get from this thing. It's called the Cartesian tree. So you take the smallest value in the whole array, the index of that becomes the root of the tree, and it splits the array into two parts, left and right. Looks familiar, right? I mean, the first name for trees was actually Cartesian trees for this reason. Now I want to compute the, let's say I want to compute the range minimum for some range. We'll do an example. Let's say I want the range minimum from 3 up to 7. Okay. Well, 3 and 7, those are nodes in this tree, right? Basically every index here appears as the name of one of the nodes in this tree. So there's 3, there's 7. Look at the lowest common ancestor of 3 and 7. It's 4. And look at that. The smallest value in this array occurs at position 4. And you can convince yourself, actually, that that's not an accident at all. This will always be the case, that you just give me, when I want to answer a range minimum query, for indices I and J, just look at the nodes called I and J, find their lowest common ancestor. The index of that thing is exactly the answer to the range minimum query for I and J. So you can take lowest common ancestor and reduce it to plus or minus 1 range minimum problem, and we can solve that. That's what we just showed. That's what we spent most of the class showing. But you can also take the range minimum problem and reduce it to lowest common ancestor, and then reduce that to the plus or minus 1 range minimum problem and solve that. So really the range minimum problem reduces to the plus or minus 1 range minimum problem. And yeah, so it's a very nice, pretty, somehow things close up nicely, and the whole picture finishes beautifully. I was reviewing these notes and thinking, oh, this is nice. So there's a structure that goes back to the 1980s that achieved this kind of space and query time, but it was complicated and messy, and no one ever used it. And I was thinking to myself, oh, but I know there's now this nice, simple, clear presentation of this thing that was invented recently. And to me, it felt recent because I was a postdoc at the time this was discovered or published by these two authors, Bender and Faraj Colton. And I thought, oh, it's really recent. But actually, it was in the year 2000. So it's still, for me, when you get to be my age, 21 years ago is recent. But there you go. Anyway, so there's a nice thing. And let's just at the big high level, let's see what we did. We ended up using this macro tree, micro tree trick again, right? We took a suboptimal data structure that used too much space. We gave it less data, just this Y sequence, these N over B elements, so that the too much space that it used was okay. And that left us with these micro problems of size half log N. That while we did two things there, we used a suboptimal structure for those. That was okay, but that by itself isn't enough. We did something more, which was to really look at these problems and say, actually, these are so small that there's not very many different problems. So we did a bit of counting here to say, actually, if you look at these little blocks here, they're so small that even if I listed out all the possible blocks, that would be not very many of them, only square root n. That's something we haven't seen before. So it's sometimes called canonical subproblems or combinatorial representation of problems. And it's really just the realization that this plus minus sequence thing is the only thing that matters. Exactly what integer you start with here doesn't matter for what we're doing. All right, so that's where we leave it for today. Yep.